So yeah, it's my pleasure to introduce Sergio Boixo from Google to give us a presentation today on their amazing recent work on demonstrating quantum computational supremacy on their Sycamore chip. Yeah, Sergio's been working on this project for years now, and I've been fortunate to have worked with him on this project for a long time, and it's been a fantastic milestone in Google's development, but also in the development of quantum computing. So Sergio, you want to take it away and tell us all about it?
Sure, yeah, thanks Mick for the introduction and for your help on getting this project going. So I'm going to talk about indeed this experiment, which was published in a paper last year. It's called Quantum Supremacy Using a Programmable Superconducting Processor. So here's the team, a lot of experimentalists and a fair amount of theorists and other collaborators. So the idea of demonstrating quantum supremacy was to choose a computational task, which in this case was to sample the output distribution of a random quantum circuit. So this was actually related and inspired by some previous work, including the work from Mick and others on sampling IQP circuits. So we were looking into that, and then we decided to make our circuits a little bit more random. The IQP circuits basically have C gates and control phase gates. So all diagonal gates sandwiched by a layer of Hadamard's at the beginning of the circuit and a layer of Hadamard's at the end. And what we did was to allow for more generic random gates in the circuit. And one reason why we do that is that the circuits that we end up with, if we do not restrict ourselves to diagonal gates between the Hadamard gates, these circuits are harder to simulate classically. So the goal is to run these random circuits on a quantum processor and collect a number of samples enough to measure the fidelity, at least in principle. I will explain how we do that. And at the same time, we perform the same computational task, so sampling, on a supercomputer eventually. So we collect in a supercomputer an equivalent number of bit streams with equivalent fidelity to the experiment. And then we compare the run times. And when the quantum processing time is always going to be short by design, because we can collect 1 million samples in around 200 seconds in superconducting qubits. But when the classical processing times becomes unfeasible in practice, then is when we basically decide we have achieved our goal. We declare achieved quantum supremacy, at least against current supercomputers and the best simulation algorithms that we had at the time, and that's when we publish our paper. So because we wanted to compare with classical supercomputers and surpass classical supercomputers, that's why we move away from this instantaneous quantum processing sampling task into more general quantum circuits that are harder to simulate. So first I'll say something about the complexity theory results behind this task. To note is that even though the computational task is to sample the output distribution, it turns out that we only know how to sample the output distribution of a random circuit. We first calculate, classically, if we first calculate probabilities. So the algorithms that we're comparing against actually calculate probabilities, but that's just because those are the only algorithms we know. The cost for the computational task in a classical simulation turns out to be proportional to the fidelity, so we do have that into account when comparing computational cost to classical algorithms. And it turns out that if you were to have a polynomial classical sampling algorithm, then estimate the probability using an NP oracle. So in probability sample efficiently, then you could estimate probabilities efficiently. And how this works is basically using some well-known result in classical complexity theory, which is called Stowe-Meyers's approximate counting. basically what it does is if you have a classical algorithm which is simulating the sampling, then you're going to have some number of random bits which are part of the algorithm. And what the approximate counting method allows you to do is approximately count the number of assignments for these random bits that gives you a particular bit string if you have an empirical. So if you can sample classically efficiently and you have an empirical, then you will estimate probabilities efficiently. And this turns out to hold even if you have globally unbiased noise. So if you believe that your noise is globally unbiased, and you have a lot of noise, you can estimate this if you want to sample under that principle. It turns out that if you're sampling with a quantum situation,
so Sergio,
when you're, yeah.
The reception's quite poor at the moment. Could you perhaps try turning off your video and let's see if just the audio works better? We kind of missed quite a bit about the sort of from this slide. So if you want to just revise some of the stuff that you talked about, then that'd be great.
Oh, okay. Yeah. Sorry about that.
No
is
problem.
It better now?
Yeah, I think
is
that's
the audio better now?
Yeah.
Okay, good. Right. So in summary, the point I was trying to make is that the computational task is to sample, so that's producing bit streams according to the probability that is defined by a random circuit. And there is a fundamental difference between sampling with a quantum circuit in a quantum processor and sampling with a classical simulation algorithm. And the difference is that if you're sampling with an efficient classical algorithm, then your sampling is a probabilistic algorithm, but you have random bits somewhere in the algorithm. And because you have random bits somewhere in the algorithm, then you can use that to estimate the probability. So even if the sampling algorithm, the classical sampling algorithm, is not giving you an estimate of the probabilities per se, it has random bits, and with an empirical, that allows you to estimate the probability. And in the quantum case, there are no random bits anywhere. Randomness in quantum sampling is intrinsic. There are no quantum bits, random bits, as part of the probabilistic algorithm. So even if you have an empirical, sampling with a quantum computer does not allow you to estimate probabilities. Is my audio clear now?
Much better, thanks.
Hello?
Much better,
good.
Thanks.
Right, so this is what is gonna allow us to separate, in terms of fundamental complexity theory, sampling with a quantum processor from sampling, which is gonna be efficient because this is a small quantum circuit, at least ideally, and sampling with a polynomial classical algorithm. Okay, so it turns out that estimating an output probability is worst case SRP hard. So this is a fairly old result. And this is sort of how you go from sampling classically efficiently to arriving to a contradiction, which is saying, well, if I can sample efficiently classically, then with an empirical, I'm able to estimate probabilities, but estimating probabilities is SRP hard in the worst case. So that means it's something I cannot do even with an empirical, and that's a contradiction. Now, worst case is not good enough because you can only estimate typical probabilities. Turns out that is also known, and this is a more recent result, that calculating probabilities exactly is also SRP hard. Unfortunately, that's not good enough also to arrive to a contradiction, meaning it's not good enough to conclude no polynomial classical algorithm for sampling, because the result that you need is that estimating probabilities in the average case or in the typical case is SRP hard, and that's a result that we don't have. Nevertheless, we conjecture that random circuit sampling is still hard. The first way we did this was just expanding the conjecture from IQP circuits by Mick and others. And there are also some other related conjectures. So that's sort of the state of the art. Nevertheless, I would like to note that without error correction, the fidelity in a quantum processor, the fidelity when executing this sampling problem, in a experimental quantum processor decays exponentially in the number of gates. So complexity theory doesn't really apply because asymptotically we just have fidelity zero, the fidelity decays exponentially. Nevertheless, all these complexity theory results are sort of important to sort of give us confidence that this problem is indeed hard and nobody is going to come up, hopefully, with a polynomial algorithm that can really do this task. So that was part of our motivation to work on this problem. So that was the complexity theory motivation. We decided to use this problem, random circuit sampling, for a quantum supremacy demonstration. The next thing we need to do is to choose a metric to sort of gauge how well we're performing on this particular computational task, on this sampling task. And for that, we developed this technique that we call cross-entropy benchmarking, which is really an estimator of fidelity. We're using random circuits. So for people that work on fidelity estimators, quantum verification and validation, this is related somehow to the standard randomized benchmarking technique, which also uses random circuits. In randomized benchmarking, you use Clifford circuits, and it's mostly used for 2-qubit gates. So we just extend that to circuits up to 53 qubits in our experiment. So we measure the fidelity of 53 qubits. Because we measure the fidelity of the whole circuit, not just 2-qubit gates or pairs of qubits, this is really now a measure of the system fidelity. So how well we're performing the whole circuit with up to 53 qubits in an experiment. And that was very important for us because it forces you to get everything working properly, not just 2-qubit gates isolated when you're not doing anything on the neighboring qubits, but 2-qubit gates when you're performing 2-qubit gates on all pairs of qubits at the same time. The measurement needs to have high fidelity, the preparation needs to have high fidelity, needs to be fast. And basically, we felt that this is a good stepping stone to go into building a fault-tolerant quantum computer. So the downside of this particular technique for estimating fidelity, cross-entropy benchmarking, that I will explain in the next slides, is that to perform this estimation, you actually need to simulate the circuit. So you're going to need to calculate, you measure a bunch of bit streams that will be clear in the next slides in the experiment, and then you calculate the ideal probabilities for those bit streams. And to calculate the ideal probabilities, you need to execute a classical simulation to get the probability. And these classical simulations becomes exponentially expensive, basically in the number of qubits. So this gets very hard to do. But on the other hand, once we start sampling for circuits that are too large to calculate these probabilities, that's when we're entering the quantum supremacy regime. Nevertheless, as we will see later, even if you cannot calculate the fidelity of the full circuit with 53 qubits, you cannot do system fidelity at 53 qubits with a full circuit. You can do something that we call patch XG, which is simply you break the circuit into halves. The halves are disconnected, so now they are easier to simulate. So you can still get the fidelity of the whole quantum computer, even if you cannot simulate circuits running on the full quantum computer with patch cross entropy. And again, that's something that will become clear when we talk about the experiment a bit more. Okay, so how does this cross entropy benchmarking work for a large system with many qubits? So the first thing we do is we write the noisy density output of our noisy experiment as a mixture between the ideal state that we're trying to build with the random circuit. So this is the ideal output of the random circuit. And some noisy operator chi, where we just collect the effect of all errors. So in the simplest case, if you think that your noise model is stochastic, then you will have these noise operators like poly operators. And then what you do is you collect the effect of applying all these noise operators in this density matrix chi. This also works with correlated errors or noise maps that are not stochastic, but that's a little bit more complicated. So anyway, this is sort of a standard equation now. P here is the depolarization fidelity, which for more than 10 qubits is basically equivalent to the fidelities, almost the fidelity with a small offset. Properly speaking, it's called depolarization fidelity. Good, so the next thing we're gonna do is we're gonna calculate the ideal probabilities for the bit strings that we measure in the experiment Q. So we measure bit string Q and we calculate probability P with some classical simulation. And then our observable is just gonna be some function of the ideal probabilities. What happens is that if we look at the expectation value of this observable, applied to just the noisy density operator chi, we're collecting the effect of all the errors. Then we get an expression like the one on the last line. And if we assume that the probabilities that we get from the noise are uncorrelated with the ideal probabilities, then we can use the central limit theorem. So we're summing a bunch of probabilities that are uncorrelated, and by the central limit theorem, what we get out of the sum is just the average value, plus some deviations from the central limit theorem that just go like 1 over the square root of the number of terms in the sum. And because we're just looking at the expectation value, the number of terms in this particular sum is just all the bit strings, so the dimension of Hilbert space. So what this means is that the expected value of our estimator does not depend, applied to the noise chi, does not depend on the details of the noise. It's just the average value. And that's what allows us to kind of forget about the noise. We don't need to know the details about the noise to extract what is the value of the fidelity. Okay, so the same thing can be said a bit more mathematically by saying that what we're doing is we have this noise density operator chi, we have some observable O, which is our fidelity estimator. And by concentration of measure, if the noise builds some sort of random quantum state, so we're kind of sampling from the Hilbert space quasi-randomly what the result of noise is, then from concentration of measure, what we expect is the average value of the Hilbert space plus fluctuations that go like 1 over the square root of the dimension. So in the context of Hilbert space, this has been used before in quantum computing. And if you think of Hilbert space as a high dimensional sphere, this goes by the name of Levy's lemma. It's the same statement as before, and it's just another way of saying that in general, the expectation value for observable, because this is a random circuit, and even with noise, it's still a random circuit. It will produce a random state, quasi-randomly sampled from Hilbert space, and by concentration of measure, where you get with very high probability is just the expectation value of your observable over Hilbert space. So as long as concentration of measure works, what you get is the following. Now, this is our observable. We apply the observable to our density output. On the noisy part, by concentration of measure or the central limit, if you want, we just get something that is independent of the noise. It's just the average of the Hilbert space. And now we need to do something else with the observable applied to the ideal output. Now, concentration of measure will also apply to the ideal output if we just choose a typical observable. So that's why we need to really fine-tune the observable for this particular ideal state, the state that we expect out of the ideal random circuit. And that's why we need to calculate the ideal probabilities. So by building an observable, which is a function of the ideal probabilities of this particular state, the ideal state, we avoid concentration of measure on the ideal output. Concentration of measure works on the noisy part. The observable and the ideal output is going to have a different value because it does not concentrate. We know both values either by simulations or analytics, and at that point we can extract the fidelity or depolarization fidelity P. So we can do that with multiple observables because all that we need is concentration of the noise and not concentrate on the ideal output. So if we choose, for instance, as an observable, the logarithmic of the ideal probabilities, this is what we call cross entropy. And then it turns out that when you average over the bit strings that you measure, you calculate the probabilities and then you take the log. You will get something that looks like the fidelity minus the logarithmic of the dimension of Hilbert space minus some constant, which is the Euler constant gamma. We used also different observable, which is the linear cross entropy. The difference is now we don't take the log, we just normalize by the dimension of Hilbert space, then -1. We call this linear cross entropy just because it follows sort of the same ideology. And it turns out that this observable linear cross entropy, well, is the max likelihood estimator of the fidelity P if you assume that the noise is fully depolarizing. So in essence, it has lower variance as an estimator of fidelity, so that's what we tend to use in the experiment. But you could do other things like the probability of heavy output that Scott introduced kind of around the same time and is used in quantum volume. So what we actually do in the experiment is we use all of them just to make sure that our fidelity estimator is working. We do calculate cross entropy, linear cross entropy, normalized heavy output, and we put that on the appendix. They basically give you the same value. And in the main plots, we just use linear cross entropy because it has a slightly lower variance. So the main assumption here was this concentration of basically that any one error average the output, so that when you take the average value with the estimator, it looks like you get the average over Hilbert space, which is the same as the average over the fully density metrics. So what we do to check if that works is we basically do a bunch of numerics. So these are numerics actually from 2016, but the paper appeared in 2018, where we ran circuits of different sizes with 16 qubits, 4x4 up to 24, 4x4 up to 6x4. In the x-axis is the depth of the circuit. So initially you're not random enough. You didn't expect concentration to work. The y-axis is the cross entropy. What we do is we calculate the cross entropy with just one poly error in every position in the circuit, and then we take the median, and the solid line is the median, and you see that the median cross entropy with just one poly error is the same as 1 over the square root of the dimension, as you would expect by concentration of measure. And there are bars here, the quantiles over discrete errors in different positions in the circuit. So in summary then, we have these generic estimators of fidelity. Linear cross entropy is the one with the lowest variance. As long as we can simulate the circuit, we can get an estimate of the fidelity for a circuit with many qubits. And the main assumption here is concentration of measure, which you can check numerically, for instance, by just dropping one error anywhere in the circuit and making sure that the value that you get just with one error is the same as the average value over Hilbert space, or the same as you will expect if you take the expectation value of the observable with the totally, the full density, the totally mixed state. Okay, so here's how the algorithm looks like, the one that we actually ran in the experiment. First, we sample a random circuit, a quantum random circuit. Then we decide how many bit strings are we going to sample in the experiment. Around 1 million. Actually, for the largest circuits, it was more like 3 million per circuit. And then we did 10 circuits, so 30 million bit strings in total. Then you run the circuit in our experimental processor. In our case, it's called Sycamore. You collect the bit strings. For the bit strings that you get in the experiment, you simulate the ideal probabilities. This is the expensive part. When you get to 53 qubits, it becomes really expensive. And then you apply your estimator. In the case of cross entropy, it's just minus the log of the, sorry, the sum of minus the log of the probabilities, or minus the log of the product of the probabilities. You normalize, and this is basically your estimator of fidelity. Okay, so the hardware this experiment was run is this processor here. It's called Sycamore. It has 54 qubits. 53 of them were used in the experiment. And it has 196 control knobs. So one feature of this chip that turned out to be very important to get the experiment to work, because we needed the fidelity to be large enough when running circuits on 53 qubits, is that the couplers are tunable. So in the figure in the left, the gray crosses, those are our qubits. They're superconducting qubits. They're versions of transmons. And the blue squares, those are the couplers. And the couplers have a control knob themselves, so you can turn them off. That makes the circuitry more complicated. It means you have, the packaging is harder. You need more cables into the fridge. You need more FPGA cards to draw your controls. So it was harder to do. But because the couplers are controllable, it turns out that you can, turn them off quite well. And that allows us to decrease crosstalk. And that's what made the experiment possible. So here you can see what is the fidelities that we measure with either cross-entropy benchmarking or randomized benchmarking. So for 2 qubits, we check that cross-entropy benchmarking or randomized benchmarking, at least on Clifford gates, they give you the same fidelity experimentally and numerically. So the black line is single qubit error rates, and we report the poly error, which is 1 minus the process fidelity. When we run isolated, meaning we only perform single qubit gates in one qubit and all the other qubits are in the ground state, the poly error rate is 0.50%. When we run simultaneous single qubit gates, which means we do single qubit gates on all the qubits at the same time, it's still 0.16%. So there is very little crosstalk in single qubit gates. For 2 qubit gates, the poly error rate that we measure in isolated mode, so that's we do a 2 qubit gate or a sequence of 2 qubit gates in a pair of qubits, but all the other qubits are in the ground state. Then we get a poly error rate of 0.36%. But what is important is the poly error rate that you get in simultaneous mode. So that means when every qubit participates in a 2 qubit gate, but still pairs of qubits don't talk to each other. So they are like a bunch of 2 qubit circuits run all in parallel. The fidelity drops or the poly error increases basically by a factor of 2. So the poly error rate is now 0.62. So there is some crosstalk when we run 2 qubit gates on all qubits at the same time, but it's not too much. It's only 0.62. And finally, the measurement error in this chip wasn't particularly good. That's something that has been improved since then. And it was 3.8% measurement error when measuring all the qubits at the same time. So this is kind of how the sequence of gates looks like in these random circuits. So we have a number of cycles. Every cycle has a sequence of random single qubit gates on all the qubits, and then 2 qubit gates, such that basically every qubit participates in a 2 qubit gate. So that's one cycle, or cross-entropy cycle. And then we repeat these cross-entropy cycles, applying 2 qubit gates among different pairs of qubits, up to some depth m, which is normally 14 for the most of the circuits, but in the supremacy circuits and the hardest circuits that we perform experimentally, we actually did depth 20 of these cross-entropy cycles, so actually 40 cycles of gates, so 20 cycles of single qubit gates and 20 cycles of 2 qubit gates. The single qubit gates, they're microwave gates, which is a standard for superconducting qubits, and they took around 25 nanoseconds. And the 2 qubit gates, turns out to be very fast on this particular architecture because it has tunable couplers, so they can be turned on and they can be turned off, and they can be turned on to a fairly high coupling value. So we could perform 2-qubit gates in around 12 nanoseconds. And the 2-qubit gates that we chose, we call them Sycamore gates. They're basically iswaps with an extra control C phase. Okay, so these are the experimental results. So the first thing to note is the black line. That's what we get, but what we call the discrete error model. So what we do is we basically multiply the probability of not having an error in any gate. We saw a couple of slides ago what was the poly error rate, so the probability of error for all the gates in simultaneous cross entropies. And when we calculate this probability of error by running gates on all the qubits, and 1 minus the poly error rate is the probability of not having an error. So if we multiply the probability of not having an error in all the gates, then we get some total probability of not having an error, which is basically the fidelity, and that's the black line, right? So this is the discrete error model, which is the main assumption, let's say, of building a fault-tolerant quantum computer, that your errors are discrete and kind of local, so you can sort of correct them. Basically, that as you increase the size of the circuit, you are not introducing more errors because there are crosstalks between qubits that are far away. So that's the black line. The circles are the cross entropy, the red circles are the result of the cross entropy benchmarking fidelity estimator for the full circuit. So up to 38 qubits, that's not very hard to do. For 38 qubits, you need to run on workstations with more than 2 terabytes of RAM, but you can just log in into Google Cloud and Google Compute and just rent one of these machines, so that's easy. Beyond 38 qubits, it gets harder. At 42 and 43 qubits, we have some results there that were done in the Jülich Supercomputing Center as part of this collaboration. And then at 53 qubits, we were able to simulate these circuits with a method that we call the Schrödinger-Feynman algorithm, or a hybrid algorithm that I will explain in the next slide. And it says here that the simulation took 5 hours. So that's basically 5 hours per circuit in 1 million cores. So 5 million core hours per circuit, and we have 10 circuits. So it was more than 50 million core hours just to get this red circle here. Okay, so the important thing to note is that, again, the fidelity from cross entropy benchmarking with a estimator running the shows quite nicely the fidelity that you will expect with this simple-minded discrete error model. We have some other data here. So something else we do as a check and as an estimator of system fidelity that I mentioned before is this patch circuit cross entropy benchmarking, and that's very simple. What we do is, let's say you have a circuit with 54, 53 qubit, you just break it in half. Basically, remove all the 2-qubit gates across this line in the middle. So what you have now is not one circuit with 54 qubits, but 2 circuits with 27 qubits. So now this is very easy to simulate because there are no gates connecting these circuits anymore. You just run a simulation of 27 qubits and then run another simulation with 27 qubits for the other half. You multiply the probabilities, that's the probability of whatever output bit string. So this was very simple to do. And again, with experimental data from PatchXCB, where we run these circuits with the gates across the cut. Those are the blue plus signs. And they also correspond nicely to the discrete error model and the full circuit cross entropy fidelity. And finally, we do something intermediate, which is we just remove some of the gates in the middle, and that turns out to make the simulation exponentially easier in the number of gates that we remove. So we call that elided circuits. These circuits are sort of in between in the sense that they are not too hard to simulate. So we tune them to be around, I think it was 100,000 core hours at size 53, something like that. So like 50 times easier or more. But they do still have, for instance, like basically full entanglement between both halves, at least if you just look at how you spread entanglement by looking at the Smith coefficients or things like that. So they're fairly complex in terms of entanglement, but not in terms of simulation. And again, we see that the highlighted circuits, which are these green X's, they also correspond to patch circuits, full circuits, and the discrete error model. So with this, we were satisfied that we were getting good fidelities. We can measure the fidelity, cross-entropy fidelity is working in different ways. The discrete error model is working. Now, but you know, the circuits that we run in this particular case, turns out we could simulate them. Basically, they have 53 qubits, but they have some hidden symmetry. So we could exploit that to simulate them. And actually, the full story behind that is when we first ran this experiment with the circuits, we thought we could never simulate them and it would be kind of impossible. But then in the process of checking in, you know, that we were correct, we tried different ways to simplify the simulation. We found this hidden symmetry. Turns out that we could simulate them, so we didn't have supremacy anymore, so we were a bit sad. But the bright side, the silver lining, was that at least we could check with full cross entropy that indeed these circuits work. So that was what we did with these 50 million core hours. And then in a couple of weeks, we found out how to remove that symmetry. So we just changed the layout of the 2 qubit gates a little bit. So we kind of removed this symmetry that allows us to run this simulation trick. And that's what we call the supremacy circuits. So for the supremacy circuits, we just decided to run only with 53 qubits at different depths. So we went from depths 12 in these cross-entropy cycles, so 12 single qubit gate layers and 12 2 qubit gate layers, all the way to 20. We couldn't do with our algorithms full circuit cross-entropy anymore, but we could do patch cross-entropy, elided cross-entropy, and of course the discrete error model, which is just calculating probabilities. And again, we see that everything aligns nicely. We publish all the data for everybody to see. So if you can run simulations with the full circuits, then the data is out there, and you can tell us if the full circuit fidelity still corresponds to our prediction. And then with our simulation methods that I will explain in the next slide, we just calculate how long it will take, what will be the computational cost of sampling if you have roughly 1 million cores to do that. So it will be around 2 hours to sample, because the sampling cost is proportional to fidelity. It will be like 1 week to do the cross-entropy benchmarking, because for cross-entropy benchmarking, we need all the ideal probabilities with perfect fidelity. But if you just want to simulate sampling, then you don't need ideal probabilities anymore, or you don't need to calculate all of them anymore. So it's a fraction of fidelity cheaper. So it goes from 1 week to 2 hours from cross-entropy benchmarking to just simulating sampling. And when we get all the way to depth 20, at least with our algorithms that are the ones that we could run, our estimate was 10,000 years in around 1 million cores. Good. So let me tell you a little bit how this hybrid simulation works, the one that we use for the 53 qubit simulation with full circuits and this verifiable circuit that had this symmetry. So the basic idea, if you remember, is we have this patch where these 2 patches, right? Like we can cut the circuit in 2. Now, when we do patch XCV, we just run circuits, choose circuits that don't have any gates across the patch. The full circuit, of course, has gates across the patches. We call those the cross gates. So what you can do is you can decompose every one of these 2 qubit gates across the patch, the gates that connect the left and the right patch. You can do an Smith decomposition. So you get an expression like this. When you have an Smith decomposition, now you have gates on the left patch D and gates on the right patch W. The problem is that you don't have only one Smith term, because then you would be done. There wouldn't be any entanglement. You could do this simulation independently, but you actually get 4 Smith terms in general with some Smith coefficients W. So if you only have one gate across the patch with 4 terms in this MIDI composition, then you actually need to do 4 simulations on the left and 4 simulations on the right. Now we have more than one gate, so we need to do a lot of simulations of the left and a lot of simulations on the right, because we need to calculate all the terms in this sum, which is the product of the Smith coefficients for the Smith decompositions of all the cross gates. So the number of terms in this sum is exponential in G, which is the number of gates connecting the two cuts. So the complexity grows exponentially. The simulation cost grows exponentially in the number of cross gates. But for 53 qubits, for the verifiable circuits, turns out that we could remove some of these gates or remove some of the Smith coefficients. So still there were not too many terms in the sum, well, only a few million, so we could simulate them. Now, how does it work if you don't want to do cross-entropy benchmarking, so you don't want to calculate the full fidelity, but you just want to simulate sampling, so you can calculate bit strings probabilities with lower fidelity? Well, then the simple thing to do is you just don't sum all the terms in the sum. You only sum a number of terms proportional to the fidelity. And we saw in a paper with Igor Markov and others that gives you a sampling proportional to the fidelity. We used to think that this was optimal in all cases. We know that this is optimal, for instance. We think that this is optimal if your noise is depolarizing. But something that has happened in recent months is that there are now these papers that have shown that in 1D, you can do matrix product state simulations, which are polynomially efficiently, as long as the fidelity, well, if you're using Control-C gates and the fidelity of the Control-C gates is not higher than 99%, then you can actually do efficient 1D simulations in 1D, but not in 2D. So for now, the cost for 2D is still proportional to the fidelity. In 1D, if your fidelity per Control-C gate is less than 90%, you can do this efficiently. If it's higher than 99%, I think it's still, the matrix product state method doesn't work anymore, so the cost is still exponential in the fidelity. Sorry, exponential in the number of qubits and proportional to the fidelity. Okay, so these are some plots from the supplement of our paper, where we sort of plot for the different algorithms that we use. What is the simulation cost? So the simplest thing that you can do is you just run what we call a Schrodinger algorithm, which is just, you just store the full wave function in memory, and then you keep applying gates to this wave function. And the main bottleneck here is the amount of memory. So if you're using RAM, which is how everybody has so far done simulations in supercomputers, then you can get up to 48 qubits. So you need a lot of memory. But then the cost is only linear in the number of gates, because applying a gate is just scanning all the amplitudes that you're storing in memory. So that can take some time if you have, petabytes, 1 petabyte of RAM, let's say. But still, is manageable. I don't remember how much, around minutes, because this is distributed around many nodes in a supercomputer. So long story short, as long as you can store your wave function in RAM, then you don't get supremacy in our definition, because you can still simulate this with supremacy. So we went all the way to 52 qubits, so beyond what you can do in RAM. Now, if you were to use Summit disk, that has 250 petabytes, so that will be enough to store the full wave function, and there is a proposal to actually do a simulation in disk. I think nobody has ever done anything like that, so that's an interesting proposal. We'll see if that gets to work eventually. So, because nobody has done that, and that's just not how you normally do these simulations, what we did when we get more qubits is we switched to this other Schrodinger-Feynman hybrid algorithm, which is the one that I explained in the previous slide. So that requires less memory, because we basically break it into patches. So if you have 1 million cores, you need to use only around 1 petabyte of RAM. So that's still a lot, but is what supercomputers have. And for the verifiable circuits, that took us around 5 hours in 1 million cores. So the numbers here in the lines in the different colors that's time for this algorithm in 1 million cores. So this was the circuit that had this hidden symmetry that we luckily found out before publishing the paper. If we jump to the supremacy circuit, which remove the symmetry, and then we increase the depth, then for this algorithm, cross-entropy benchmarking will be like 1 week. For the 12, up to 600 years to do in-depth 16. So we didn't do that. That was too expensive. And for sampling was 10,000 years. So that's what we published. Now, we also said, of course, that the algorithms will keep improving. So eventually, the simulation cost will decrease and hardware will improve. So eventually, maybe somebody's able to run these simulations and hopefully report cross-entropy for the data that we publish. But it's very important to actually run your algorithms. So, you know, we worked very hard to actually run in an experiment in a quantum computer. And, you know, in computational numerics, you know, it's also standard to actually run an algorithm, not just report a proposal. So that's what we're comparing against. And I will talk about some algorithm that was run recently, which is basically a version of tensor networks. Okay, so to simulate quantum circuits in tensor networks, the first thing you do is, here's the standard representation of a quantum circuit with a single qubit gates and 2 qubit gates. And you can think of the gates as tensors. The 2 qubit gates will be a tensor with 2 indexes as input and 2 indexes as output, for instance. And now the cost of calculating one probability, sorry, the algorithm to calculate a probability is basically a tensor contraction where you need to contract the indexes of all these tensors. The tricky part of doing a tensor contraction is to choose in what order you are contracting indexes, right? Because what you want to do is when you contract indexes between 2 tensors, you tend to get tensors with more indexes. And if you start getting tensors with too many indexes, then your tensors are too big. They don't fit in RAM in a supercomputer anymore. But maybe there are other orderings where, you know, you start contracting tensors, but they have many indexes in common and the size of the resulting tensors doesn't grow too much anymore. So that's a hard problem. And there was some recent advances in doing this in a paper by Johnny Gray and Curtis. So what they did is basically they used some heuristics to find optimal tensor contraction orderings. They call it hyper-optimized tensor contraction. So the heuristic that works the best is this algorithm K-high-par, which is based on community detection. The details are not incredibly important for this particular talk. The main point is that with these heuristics, they actually improve substantially the tensor contraction ordering, and consequently, they improve the runtime also significantly. So these are the runtimes that they report. Basically, for our circuits, the hardest ones, Sycamore with 53 qubits and depth 20, they were able to run, well, not all the contractions that you will need for a full wave function simulation, but a fraction of them and all the contractions. They kind of divide this large contraction into chunks, all of them sort of the same cost. So they do a fraction of them in 1 GPU. And they calculate that it will take 7 billion seconds to calculate one amplitude with 0.5 fidelity. So that's 7 billion seconds. Now this is on one NVIDIA GPU. If you were gonna do this in Summit, which has 28,000 GPUs, that will take 3 days for one amplitude at 0.5 fidelity, but it will actually be probably lower for several reasons. One of them is the GPUs in Summit are better than the GPU that Johnny Gray had in his workstation, so maybe it will be 4 hours, or maybe it will be even less, because in Summit, maybe you can organize the contractions a bit more efficiently because you have more RAM. So anyway, with this, the estimate for sampling at 0.2 fidelity as in our experiment becomes 3 years. So this is already quite lower than our 10,000 years, so they clearly beat us. For doing cross-entropy, will still be 1,000 years, so a bit better than the hybrid algorithm, which gives you ideal probabilities. But you know, the significant part is they actually go from 10,000 years to 3 years now with these optimized tensor contraction orderings. Okay, so that's where we are in terms of simulations. So what have we learned out of this experiment? A few important lessons, I think. One of them is that at least with this Sycamore chip, which has controllable couplers, so you can turn the couplers off, we get the same fidelity for full cross entropy as predicted by the discrete error model or patch XCB. So the fidelity does not seem to depend on the amount of entanglement, because patch has half the entanglement of full circuits, for instance. And it does not seem to depend on computational complexity, because it's very easy to simulate these patch circuits, but it's very, very hard to simulate these full circuits. So that's good. Fidelity seems to be physical and unrelated to computational complexity or entanglement and things like that. The discrete error model works, at least to the level of precision of this experiment. We will need more precise experiments. There might be correlated errors, which are 10 times lower than the errors that we see. We wouldn't be able to see them in this particular experiment, but at least for the level of precision of this experiment, the discrete error model works. And this is, again, the model that is used in fault tolerance. So if it works and the errors are low and the discrete error model works, you can build a fault tolerant quantum computer. We sort of expand the frontier of highly complex quantum states by around 10 orders of magnitude as compared to previous experiments. And we kind of challenge the extended truth-theory thesis in the sense that, what the extended truth-theory thesis says is that all computational models are equivalent in the sense that they can compute the same functions efficiently. So the extended part refers to the efficiency. They are the efficiency of all different computational models are the same. We believe that that's not true in quantum computing. And in this particular case, well, we ran an experiment that so far nobody has been able to replicate with a supercomputer, even though the experimental quantum processor is like a 1 centimeter square. Well, it needs a fridge, which is bigger, but the chip itself is just 1 centimeter. We are comparing against these classical processors, which basically are 2 basketball courts size of chips stacking racks. Okay, now my last 2 slides. This is indeed a general quantum processor. So we recently published one experiment on quantum simulation of a hydrogen chain. This is a hydrogen chain in the Hartree-Fock basis, basically. That means it's a mean field state of what we use by design. So you can simulate it classically. But the point of this experiment is sort of calibrate our chip or measure how well our chip is performing. So this was an experiment with 12, the biggest ones had 12 qubits, sort of simulating 2 hydrogen atoms in the Hartree-Fock basis. And we look at the dissociation curve as a function of the bond distance between the different, the 12 hydrogens in the chain. What is really cool, I think, about this experiment is that if you, first, you get a bunch of bit strings because you always measure, you get bit strings, that's always what you get. The way the experiment is designed, we start with half occupancy, so 6 qubits 1, 6 qubits 0, or 6 electrons if you want. And the gates that we perform are for many gates that conserve the number of particles, so we can post-select, meaning we eliminate bit strings that we measure if they don't have the right number of electrons. So those are post-selected bit strings that increases the fidelity a little bit. And then you can, in this particular experiment, purify the state that you get. So you measure a bunch of bit strings. We're measuring the 1 reduced density matrices, observables, and we sort of purify them. We purify into the closest, purest state consistent with the observables that we measure. And that increases the fidelity dramatically by more than an order of magnitude. So I think that's what is kind of cool about these proof of concept experiments. You check that your experiment is working, you're learning, how to implement more complex gates, But mostly I think you're learning about error mitigation techniques, which are indeed going to be necessary if we want to do quantum simulation, for instance, on noisy intermediate scale quantum computers, because they still have too many errors. But maybe with error mitigation, we can get into a regime where we can do some interesting quantum simulation experiments, hopefully beyond what you can do with classical techniques. With this, I would like to conclude. Thank you.
Thanks very much, Sergio.
Hey.
Virtual clapping is kind of hard to do.
Virtual clapping, now. Yeah. I thought for a second maybe it wasn't my own now.
Thanks so much for your talk. I guess I should open up now for see if people have any questions I'd like to ask Sergio. So if you do, maybe unmute yourself and ask away.
Maybe Sergio can turn on his video now too.
Oh yeah, it might work.
All right.
Now. See how we do.
Do
I'm going to turn off my video because people should see Sergio, not me.
Okay, let me know if the audio starts failing again.
Yeah. Actually, we had one quick question. I missed the definition of what the difference between the full circuit and the elided circuit was.
Right. So basically, yeah, in the full circuit, we have 54 qubits. You can imagine that for this hybrid algorithm, this Feynman circuit algorithm, what we do is we're going to cut the circuit in half. So we're in the middle, right? Like around this half. So we're going to cut a lot of 2-qubit gates that are connecting these two halves. So we want to cut the circuit into halves, but the problem is that there are 2-qubit gates in the middle. So the 2-qubit gates in the middle are the ones that we have to simulate by doing a Smith decomposition. And the cost of this simulation is exponential in the number of gates that we cut. So what we do on these elided circuits is because we know we're going to be simulating these algorithms by cutting them in half, and we know what are the 2-qubit gates that we're going to have to cut, and the 2-qubit gates that we're going to have to do a Smith decomposition and then do all these independent simulations for all the different Smith terms. So what we do in the elided circuits is we put only, let's say, half of the 2-qubit gates across the cut. So this is enough to sort of create fully entangled states in the ideal case. But because we remove half of the gates in the cut, and the cost of this hybrid algorithm is exponential in the number of gates in the cut, we can make it so the simulation is now quadratically easier, for instance. And those are the circuits that we call elided circuits. They're just fine-tuned to, be as easy to simulate as we want them, but still not fully trivial. So the trivial ones will be like the patch circuits where we just remove all the gates on the cut. So we now have 2 independent circuits, so that's very easy to simulate.
So in some sense, it allows you to have the state complexity without necessarily achieving the computational complexity.
That's correct. Indeed, yeah. For
really
the elided circuits, we actually check that we get, the Porter-Thomas distribution and things like that, right? Formally, if you just look at, I don't know, the propagation of entanglement in terms of counting Smith weights across the cut and things like that, in theory, we could have a fully entangled state. So as far as we can tell, the state is sort of as complex as with a full circuit, but because we remove, let's say, 15 gates, now we can actually simulate it. And we only remove a small fraction of gates, right? Just 15 gates across the cut, that allows us to simulate it.
Yeah. No, that's really interesting. All right, thanks, Sergio.
So thanks.
So do we have any more questions?
I don't know if there are any questions in the chat, which I didn't check as I was talking.
I actually have a question.
I guess not.
I want to know a few good answers. But in your hydrogen chain simulation you showed towards the end there, which was super interesting, did you manage to have slightly better measurement fidelities on that simulation than in the Supremacy results?
That's a good question, and I think not actually. This is pretty much the same chip, for the data that we publish. I'll have to check because, yeah, I'll have to check. Actually, there are several chips in the lab, and I don't remember what particular chip was used for this experiment. So that's something I'll have to check in the paper. I think if you go to the appendix, you will probably see the measurement error, and you can check if it's less than 3.8%.
Okay, thanks very much. The post-selection trick's really cool, actually, for this kind of simulation.
Yeah, the post-selection works well. The projection to a pure state, that works wonders in this particular case. So it will be, it's a little bit fine-tuned to Hartree-Fock because it's a projection using one reduced density matrices, but you can do similar things with two reduced density matrices and things like that. So I think as a proof of concept, I think this is a fairly, this is quite a promising direction. And I think we're gonna need these tricks and more to, get the fidelities that we need for quantum simulation. So I think, error mitigation is a very important area of research.
So following on from this, from Mick's question, just the red curve is obviously actually using the quantum chip to do variational quantum eigensolving of the problem. Are the blue and green lines also experimental data, or are they then the predicted values from the simulations using these tricks?
Yeah, that's a good question. Sorry, I went very fast over this slide. So all the lines are experimental data. The difference between, okay, so for green and blue, because this is a mean field model, what are the optimal values in your circuit, right? Ideally, because you can simulate it. So green and blue are using what you think are the optimal values for your gates. And red is, you do variational quantum eigensolver. Basically, you do a gradient descent of your energy. And it turns out that the optimal values for your gates are not the ideal values, and that's probably because you have some coherent errors, right, in the circuit. So that allows you to remove coherent errors or control errors and increases the fidelity a bit more or decreases the energy a bit more because you're removing coherent errors. And it's one of the nice things about these variational algorithms that you can remove coherent errors. But all the curves are experimental data.
Okay, thanks.
By the way, kudos to Nick and Ryan, who are the ones that work on this experiment the most. Ryan Babus and Nick Rubin.
Thanks.
Okay, so do we have any more questions? Just unmute yourself and ask.
Hi, Sergio. I have a question about supremacy readouts. So you said that the circuits have depths of 22 qubit gates, right? And this is like, I must have missed something, but it's looked like a very low depths circuits. Like, how do you justify that's hard, or what's I think there's something I'm missing. How you can argue that this low depth circuits are.
So let's see. Yeah, that's a good question because we changed the way we explain it on the paper a little bit, and that's what they use in the slides. So these circuits have 20 what we call cross entropy cycles. Every cycle has single qubit gates and 2 qubit gates. It's really depth 40. So that's one thing. If you compare with like the circuits in our first theoretical paper, those circuits, they had they were less dense, so they have less 2 qubit gates, twice less. So this depth 20 will actually correspond to depth 80, I think, of the, actually no, it will still be, no, sorry, it will still be depth. This depth 20 will correspond to the 40 of the previous circuits. Because we have now more 2 qubit gates. We only need to do 4 layers of 2 qubit gates to complete a 2D lattice. Whereas in the previous papers, when we were looking at sort of the recycle architecture, we needed to do 8 cycles to complete a 2-qubit lattice. So there was a factor of 2. So this depth 20 is actually the equivalent of depth 40 in Bristlecon. And then another difference is that the gates that we're using, which are kind of ISWAP gates, they're roughly twice as hard to simulate as Control-C gates. And that's a 2 in the exponent. So this depth 20, which is really depth 40 if you were looking at Bristlecon, because we're using these gates that are more complex, meaning they have 4 Smith terms instead of 2 as Control-C, then it's really like depth 80 in the Bristlecon circuits. So long story short, I know it's confusing. When we say that 20 for cross-entropy cycles and these Sycamore gates, they are as hard as depth 80 on the Bristlecon Control-C circuits that we were benchmarking for a couple of years. I don't know if that's part of the confusion. How come we were talking about simulating depth 40 and now all of the time we're doing depth 20? But the other way to answer your question is, how do we know it's hard is because we kind of work quite hard on algorithms and, simulation algorithms. So they are hard because...
Yeah, that's actually my second question. You mentioned several classical algorithms, one being like you prepare the state vector and store it in a hard drive. And, but like, so what are the classical algorithms simulating? Like, are they doing the sampling problem or the computing some probability distributions, or like computing the
so if you manage to, right, if you are, if you can save the full wave function in disk, then you don't save anything by just sampling with lower fidelity because it's this, the full wave function anyway. So as far as I can tell, at least for all the algorithms that people, have implemented and used and discussed, if you store the full wave function, it's always a perfect simulation. Now, for these other algorithms that are based on tensor networks, here you can actually tune the cost to the fidelity that you want. So when I say here that this is, using the numbers from Johnny Gray and Curtis, is 7 billion seconds in 1 GPU. That's at 0.5 fidelity. If you wanted to, that's 1 amplitude at 0.5 fidelity. If you use the same algorithm, but you want to calculate 1 amplitude at perfect fidelity, then it will be 200 times harder. So you will have to multiply 7 billion seconds by 200. So, so this algorithm, the cost of running this algorithm is actually proportional to the fidelity that you want. So when I say here that you can do 3 million amplitudes in 3 years of Summit, that's for 0.2% fidelity. If you actually wanted to do perfect fidelity, then it would be 500 times more expensive. So that's around, 1,000 years or something like that.
Okay. But like
so
they are doing the sampling problem, like giving the strings with high probability, or they are computing the amplitude for several set of strings. What are the problems they are solving?
Right. The problem is always sampling, but classically, all the algorithms that we know for these random circuits, you actually first start by calculating probabilities and then you sample.
Okay.
Now, you don't need to calculate all the probabilities though. You basically, it's more than good enough if you calculate 10 probabilities for every bit string that you output. And so what you do is you basically do rejection sampling. And there were some papers first on the context of boson sampling that they mentioned, well, because the first sort of very gross estimates of what is the computational cost to simulate boson sampling was just, well, what is the cost of estimating the full wave function? But then people started doing simulations where they will just calculate 1 amplitude, which is proportional to the determinant by definition of boson sampling. And then if you're sampling, well, one amplitude is not good enough to sample, but then you calculate a few and you do rejection sampling. And it turns out that in the case of boson sampling, you need to calculate around 100 probabilities per output bit string. In the case of random circuits, it's good enough to calculate 10 probabilities per output bit string. So if you want to produce a 3 million bit string for sampling, then you only need to calculate 30 million probabilities. But if you're using this algorithm, tensor network contractions, you don't need to calculate ideal probabilities if you only want to sample at 0.2% fidelity.
Okay.
So the computational cost is 500 times cheaper for sampling than for calculating the probabilities exactly.
Okay, thank you.
Sure.
Okay, maybe we should wind it up there. That was a really interesting discussion. And thanks again, Sergio, for the presentation you've given us today. And thanks for taking your time out to let us all hear about the really interesting work which has been going on at Google over the last few years. So yeah, everyone, thank Sergio again, virtually, however you're going to do it.
All right.
And
thank you.
Thanks again.
Thanks a lot. Thanks for the invitation. Thank you.
Thank you.
Take care.
Thanks.
Bye.